We also can see that you're going to have air masses bumping into one another, and literally air masses riding up and over one another, where more dense air masses will stick to the surface and less dense air masses will ride up and over the denser air masses. And the transition zones between those air masses, those are our weather fronts. Our cold fronts, our warm fronts, our stationary fronts, and our occluded fronts are all transition zones between air masses. So a front, as we have defined numerous times in this class, is a transition zone between two air masses of different densities and are known as elongated areas of low pressure. So areas of convergence. Upward motion occurs over fronts. Typically, it is temperature differences that define the front, such as a cold front or a warm front, but sometimes fronts separate air masses of only different humidity. I mean, the temperatures are about the same, there's just a humidity difference over an area, and that's what the front separates. Fronts have both horizontal and vertical extent, meaning looking at the surface weather map with our mid-latitude cyclone over the Great Lakes, an occluded front extending south, a cold front, then a warm front, and even a stationary front well back to the west. This is a surface weather map, and this gives you the illusion that fronts occur at the surface. But fronts not only have their horizontal extent that you can see, the elongated area of low pressure, but they also have vertical extent. They go up in the atmosphere. So fronts separate the five air masses from one another and are zones of lower pressure. They're troughs of low pressure. Fronts are classified as to which type of air mass, cold or warm, is replacing the other. For example, a cold front shows the leading edge of cold air displacing warmer air. And if you look at the front, you have a line, whether a red line or a blue line or a purple line, and then you have these funny shapes, triangles on the cold fronts and little half circles on the warm fronts. Those triangles are known as barbs, and the half circles are known as pips. And the direction that either the pip or the barb is moving is the direction the front's moving. So if we look back at our surface weather map, our warm front is moving from the southwest to the northeast, just basically on top of that area of high pressure with that clockwise flow around the high pressure, pushing that wind to the north from the south and southwest, and it's moving off toward the northeast. So our pips on our warm front are showing the front moving to the northeast, whereas the cold front, the cold air is wrapping counterclockwise around our area of low pressure over the Great Lakes, and that cold front is bringing cold air from Canada around the high pressure over Canada with the clockwise flow, and then down into the southern states on the backside of the low pressure with the counterclockwise flow. And the pips on that cold front, stretching from Kentucky back into the panhandle of Texas, are showing the movement of that cold air south. Now, looking at that stationary front stretching from Montana back into Texas, it is alternating pips and barbs. So that's showing that that front's not moving, it's stationary. And you can see that the winds are blowing from the southeast on one side, the northwest on the other, and almost blowing parallel to one another, which is why the front is stationary. And essentially what you're seeing is two air masses, both polar, so both cold, but the one over the plains being a dry continental air mass, and the air mass over the Pacific Northwest being moist. And that's a good example where these cold fronts are not separating temperature differences, but separating humidity differences. So here is our cold front. Two different depictions of the cold front. On the upper right, we just see one front with cold air, followed by a second front of very cold air. Both are moving from left to right, and we can see the pips on the fronts moving, showing that direction. And then out ahead of the polar front, that warm air is flowing up from the south. So a cold front is a transition zone in the atmosphere where an advancing cold, dry, stable air mass displaces a warm, moist, unstable air mass. And whenever you move cold air over warm air, so you take cold air, you move it over a warm surface, you warm that air at the surface, that destabilizes the atmosphere. And looking at that lower illustration, you can see the result of the unstable atmosphere creating clouds with vertical extent, our cumulus and our cumulonimbus clouds. So advancing cold fronts will have cloud cover well out ahead of the cold front. And you have very defined cloud patterns and precipitation patterns associated with cold fronts. This cold front at the surface is showing a southerly flow out ahead of it with 50-degree temperatures and a northwesterly flow behind the cold front with temperatures between 39 and 42 degrees, and even much colder as you go further off to the north and west. That warm, moist air is literally scooped up, almost bulldozed up by the denser cold air, and as it's lifted up, it cools by expansion until the temperature reaches the dew point, which in this case is 32 degrees. Once the temperature reaches the dew point, It has 100% relative humidity and saturation, further lifting along that front, creates condensation and cloud formation. Condensation is a warming process, further lifting those parcels. And again, that unstable atmosphere, you reach the level of free convection and you get these towering cumulus clouds, which along cold fronts can produce not only thunderstorms and heavy precipitation, but lightning and severe weather in the form of hail and potentially even tornadoes.
The cold front represents a boundary where cold air is replacing warm air. As the cold front moves along, warm air ahead of the front is lifted along the frontal boundary. The rising warm air often condenses into huge thunderstorms that produce heavy rain, strong gusty surface winds, and occasionally hail. As the cold front passes, the wind shifts, temperatures drop, and precipitation usually ends as drier air moves in behind the front.
We can determine the location of a cold front by cloud patterns, and we can determine the location of a cold front based on precipitation patterns. As we see in the radar imagery to the bottom left, along and ahead of the cold front is where we find the showers and the thunderstorms with a little bit of lingering rain behind the front, but then very rapid clearing. And of course, that's going to result in a cloud pattern of towering cumulus clouds just along the front, out ahead of the front, high clouds, and then behind the front, clearing cloud cover. If you were looking for a cold front on a surface weather map, if the blue cold front had not been drawn, take a look at the surface weather map on the right. We're going to focus where the cold front crosses the Tennessee-Mississippi border. And we can see several things that happen between the areas to the south and to the north, the transition from the warm air to the cold air of the cold front. We have sharp temperature changes, sharp moisture changes, a wind shift, and pressure changes. So the two station plots we're looking at, northern Mississippi and then southwestern parts of Tennessee. And in northern Mississippi, the temperature is 50 degrees and the dew point is 48 degrees. So there's a very small dew point depression. The dew point's very close to the actual air temperature, and so we can see that it's relatively humid air, and there's lots of moisture there. The R with a little arrow underneath the 50, that represents thunderstorms. Of course, the circle filled in represents the cloud cover. And the most specific thing you can see with the frontal passage is the winds are from the south and west at about 15 knots. Just to the north, not very far away, in southwestern Tennessee, we have a 39-degree temperature. The precipitation is more just showery, but most specifically, the winds have shifted, clocked all the way around the north and west, and they've picked up to about 25 knots. Now, if you move further to the north and west, we're going to get up into northern parts of Arkansas. We can see where the temperature is even colder, and the dew points have dropped. The winds are there from the north and west as well. And then once you get way on up to the north, into areas like Missouri, you can see where the cloud cover has begun to clear, and we have a 24-degree temperature, a 17-degree dew point, so much colder, much drier air, and that northwest wind as well. Out ahead of the cold front over southern parts or central southern parts of Mississippi and Alabama, we have that southwest flow of warm, moist air, and behind the cold front, that northwest flow of cold, dry air, all part of the counterclockwise flow into the low that is the parent of this cold front. A warm front is the transition zone where advancing warm subtropical air from the south and moist air is replacing or retreating cold, dry polar air mass. So with a warm front, you have warm, moist subtropical air from the south, and it's moving forward to replace an area of cold air, cold, dry air, that's moving back to the north. And so the warm front typically is moving from southwest or from south to north. Out ahead of the cold front, to the north of the cold front, there's generally an easterly flow and colder air. To the south of the warm front, you're going to find that warm, moist air. The cloud and precipitation patterns are quite a bit different, but essentially you're going to see a similar type of transition from one side of the front in terms of wind shifts and also temperature and humidity gradients, or temperature and humidity differences. So if we look at the illustration to the left, the cloud formation and the precipitation is a function of what is known as overrunning. So think about the warm, moist air that's advancing and overtaking the cold, dry air. Warm, moist air will be less dense, so it will ride up and over that colder, drier air, and that's what is known as overrunning. As opposed to the cold front, in which the cold and dry air is replacing the warm, moist air, and that cold, dry air literally lifts that warm, moist air straight up. With the warm front, that warm, moist air of the advancing warm front is sliding up and over your cold air that is receding. And so when you have cold air at the surface and warmer air aloft, that is going to be a stable environment. That's a stable environment. The cold air, if lifted, will tend to be colder than the air above it and will want to sink back down to its original position. So what you get is those stratiform clouds. Stratus, the nimbostratus, where the rain then transitions into snowfall, and then just some high cirrus out ahead of it, and much, much colder air. So if you look from south to the left, to north, to the right, you have that cold air that is receding. As that warm air approaches, the warm air rides up and over it, creating a stable environment. Flat stratus clouds, eventually those clouds get thick enough where they produce rainfall, then cold enough where they produce snowfall, and then way out ahead of it, you have that much colder air. If you look at the surface map to the right, we can see that behind the warm front is that typical south, southwest, maybe even southeast warm, moist airflow. You can see the dew points and the temperatures in that region are quite, well, the dew points and the temperatures are higher, and you have a very low dew point depression indicating high relative humidities. And the winds from the wind barbs you can see are from the south and southwest. And then out ahead of the front, those winds shift to the south and southeast. And eventually, well north of the front, you can see them on the upper left, where we have some snowfall. Those winds are beginning to shift east, and eventually they'll shift to the north and east. So that wind shift is a very, very specific indication of a frontal passage. And remember, because the winds are moving in two different directions, those winds are converging at the surface, and that's also the lift that pushes that warm, moist air up and over the cold air, and how we get the warm, moist air at the surface to its dew point, to 100% relative humidity, to condensation, cloud formation, and eventually precipitation.
A warm front represents a boundary where warm air is replacing cold air. The clouds that form along the frontal boundary may extend far out ahead of where the front is touching the Earth's surface. In winter, as the cold front approaches, precipitation may begin as snow, which often changes to sleet or freezing rain, and finally to rain. As the warm front passes, temperatures rise, winds shift, and precipitation usually ends. In the warm air behind the front, scattered clouds often form.
Stationary fronts are when two separate air masses of different densities, so one could be cold and one could be warm, or it could just be humidity differences causing the density difference. Remember, more humid air is going to be less dense, drier air is going to be more dense, warm air will be less dense, cold air will be more dense. So frontal zones are transitions between air masses of different densities. So a stationary front is where those two air masses are not moving. They're just sort of rubbing up against each other. The winds will be coming from two different directions, so that frontal zone, that transition zone, that front, that stationary front, will be an area of low pressure, elongated area of low pressure, and will provide lift. And so lift will generate cloud formation and precipitation. But generally, the precipitation is much closer to what you would find over a warm front. So not quite stratiform, a little bit of vertical development, and maybe you'll have some thunder, but typically closer to what you'll get with a stationary front, more just that showery precipitation. Stationary fronts are then transition zones between two air masses that are not moving or are moving very slowly. So rarely is a stationary front dead stop. Typically it's sliding one direction or the other, or sometimes it's kind of moving back and forth, undulating slowly. These two air masses will sometimes interact along a stationary front, agitating the atmosphere, and that boundary will have some showers, even a thunderstorm, but generally there's not any warm air or cold air moving. The weather along these fronts is similar to warm fronts, less turbulent, sometimes even much, much longer lasting. You get a stationary front, it doesn't move, it can stick around for a couple of days, where a warm front typically is moving to the north. Now, we do see this in our